continue with the problem of free convection that we discussed, and the importance of the so-called Gaussian approximation, which takes into account the temperature dimensions on the density. So the system here is really an enclosure surrounded by two balls which are each at different speed, and we saw that since there is no force flow, the energy balance would simply reduce to a typical one-dimensional convection equation and gives rise to a linear velocity profile. And so this is the coordinate system chosen in coordinate Lightfoot. So this is y equal to minus 3 and y equal to plus 3. So this is the origin. So if you apply the momentum balance, so the first step is actually, since the nature of the problem is such that the energy balance is effectively decoupled from the momentum balance, and what we get here is a simple expression for the linear profile, which can be given as E into T bar minus half delta T y over V. The T bar is the average of the two temperatures, and delta T is T2 minus T1. This is the temperature profile. Now when we apply the momentum balance in the x and y directions, we simply give the pressure to be independent of x and y. Right now for the pressure, so the net result of the x and y momentum balance would be that P equal to a function of z alone. Then we go to the momentum balance in the z direction, and so the inertial terms can all be shown to vanish identically, and so we get 0 equal to minus dE by dz minus rho g plus let's also assume that the velocity moment in the z direction alone is non-zero. It depends only on y. And so then here is where the Gaussian approximation is used. Right? So this is the Gaussian approximation. And then what we have to do is to substitute for t minus e bar from this, and then the final differential equation can be rearranged as this is all done yesterday, so I'm just realizing what we did. Minus rho bar beta bar g by 2 delta t to b actually y is equal to dp by dz plus equal to this is a function of z alone, and this is a function of y alone. Right? So the two can be equated to a constant given by C1. So the glaring contradiction here is, on the one hand, something like this clearly comes from a relation such as this. So we suppress the pressure dependence. Right? Clearly this is coming from an equation of state. Otherwise thermal expansion coefficient cannot really be brought into the picture. And however, we continue to treat here the pressure as a mechanical variable, ignoring the fact that the pressure is not in. So this seems to have give the impression of what is usually assumed for compressible fluid, whereas this seems to have something that is done for an incompressible fluid. So there is a contradiction. We have not satisfactorily resolved it. So it is following what is available traditionally in the standard textbook. And so we proceed with that. So our main concern is with this, integrating this twice. So I'm combining this with this constant C1. So integrate it twice, then I will get the following expression. get three constants on top of C1. We get two other constants. So it's a cubic in Y is what we have here. Two of the constants I said can be determined by the no-slip boundary condition. Effectively, you can determine only one constant unambiguously, and we seem to get a relation between the other two constants. So if we said equal to 0 at y equal to plus or minus b, those are the two conditions I get. So if I apply it first to plus b, I get bq plus c1 b squared plus c2b plus c3 equal to 0. That's the no-slip condition applied at y equal to plus b. This is again the assumption of no-slip condition is what is normally done for a linearly viscous incompressible fluid. That's what is done here. And so then finally, at y equal to minus b, if I apply that, then I get to minus bq plus c1 b squared will remain the same, minus c2b plus c3 equal to 0. We get two equations with the three constants. So the easiest thing is to simply add. If you add the two equations, then I get this important relation that C3 is actually equal to, if I add this will cancel, this will also cancel. So I get 2C3 plus 2C1b squared equal to 0. So that means C3 equal to minus C1b squared. We get a relation between C3 and C1, right? And then C2 can then be determined. So we go back to either of these expressions, then become equivalent to each other. And so C2 can be determined with either of the expressions. So C3 plus C1 b squared is 0. So C2 then can be determined unambiguously, right? So C2 would be minus rho bar beta bar G by 12b bq, and then another b in the denominator, b squared. So I get a b in the numerator. So 12 times b is what I get for C2. And of course C1 is known in terms of C3, so I can choose to retain C1 and then finally get the expression of velocity in terms of the single constant C1. So that will be 1 over viscosity times. So effectively I have this, and I also have C2 given by this. So those two terms can be combined, and I can just write the final expression. The rho bar beta bar G by 12b delta t, write it in a more familiar form, b squared times y over b cubed minus y over b. Right? So that is obtained by combining these two terms. C2 is very much related to this coefficient. So I take a b squared out as common, and then I get y cubed by b cubed minus y over b. You can easily verify that. Right? So that can be easily verified. And then I have the other term, which would be minus C1b squared times 1 minus. So I am combining here these two terms by substituting for C3 from here. So I have C1y squared minus C1b squared, which I am writing as minus C1b squared, then 1 minus y over b squared. Okay. So that completes the expression for each. And of course C1 has to be determined. If you work out typically, the C1 was determined by using this in earlier problems on the incompressible fluid, and C1 is finally expressed in terms of pressure difference, or a modified pressure difference. That's not what is done here. Instead, BSL imposes an extraneous condition that there should be no net mass flow at any cross section. So that translates then to integral minus B to B rho dz dy equal to C. Of course, another dimension would be, the mass flow is in the y and then also in the x direction. That integral will just cancel. You get the breadth of the plane, right? It's not going to contribute. You get a net effect of that. So, if I substitute, then I have to effectively I have Ez here, and for rho I have to substitute rho bar. Whatever I have there, rho bar times 1 minus beta bar times E minus P bar. This is an integral over y, and so again I have to substitute. So rho actually effectively would be given by, in terms of y, it would be given by rho bar times 1 plus beta bar delta T by D times y. So I have to substitute for rho here. So, and then I have Ez, and then I have to integrate it. If you look at this has 1 plus beta bar delta T by 2y. So let's look at the terms that we will get in this integral. So it will be minus B to B. Right? So one of the terms would be, so I have to multiply, so 1 over Q can be taken out. It's a common factor. So what you will get is rho bar times one of the terms would be rho bar times 1 plus beta bar delta T by 2d y times this, right, times minus C1 b square, right, times 1 minus y over b square. That will be one of the integrals. The other integral would involve multiplying this with this term. Right? So I have taken this. There are two terms here basically. One involving this y cube by minus y, and this 1 minus y squared effectively. Right? So, so that completes this term. Now, if we look at multiply this with this term, you will get two terms effectively. One multiplying one with this, the other multiplying the second term with this, and that's what he says has to be neglected, because that term, this multiplying this, will lead to a delta t squared. And so, since terms involving higher order in delta t, the t minus t bar is nothing but would be the first order term. So t minus t bar squared would bring in delta t squared. So he says that those should be actually not taken into account to be consistent with the Boursin's approximation. Right? So we get that the next term would be 1 over q would still be there, and then I have integral minus b to b, and then I have rho bar beta g by 12 b delta t. So I have already another rho bar times 1 plus, I don't have that, so that would be rho bar alone will come in, and then I have b squared times y over b whole cube minus y over b dy. Now you can easily verify that this integral would actually be 0, because you are integrating y cube effectively from minus b to b is 0. It's an odd function. Minus b to b would give 0. Y also, to integrate from minus b to b, that will also that is first evaluated at b square. So that would be b square, right, by 2 minus, and again minus b square. So anytime you have an odd function, you are going to get square, and similarly for y2 you get y power 4. Then that is evaluated between the two limits minus b and b. That would again give c. That interval would be 0. Now for the same reason, this term multiplying this will be y, right? I can take this as y over b. So this would effectively be y over b minus y over b cube integrated from minus b to b. That again will be c. The only term that will finally be left is 1 over rho r times minus c1 b square times 1 minus y over b square dy. So you can easily verify that 1 minus y over b square dy will not be 0. Integral from minus b to b. After all, integral of 1 is going to give b minus b. So that will be 2b. Similarly, you will get y squared, the integral will be y cube, and that again will add up rather than getting subtracted. So this is, when you take this to be equal to 0, this effectively implies that c1 has to be 0, but the integral is not 0. Only coefficient that is left is c1, right? So it is effectively c1 times some integral. That integral you can easily verify is not 0. Integral is effectively 1 minus y over b squared dy. That is not 0. So since the whole integral must be 0, we have talked of already both the terms, the integrals themselves vanish. Finally, what is left is c1 times an integral. That integral can be easily verified to be non-vanishing. So from that we conclude that c1 is equal to 0. And I finally get in this, I don't have to consider this term. What I have for the velocity profile is simply given by this, and you can easily verify that that velocity, we have already verified that it is going to vanish at the two ends. You can easily verify that y equal to 0 also, that will vanish. So the imposition of the third condition, the extraneous condition, if this is y equal to 0, can easily show to lead to a velocity profile that is given by this, like this. You can easily find out what the maximum velocity would be, right? So this is the velocity plot, right? So this is the velocity plot. This is how it will look like. So there will be another point in between where it will vanish. The imposition of this condition imposes the symmetry between with y equal to 0 as the, you can say, as a plane of symmetry, right? That will lead to a velocity profile. So this is somewhat approximate treatment of the whole problem. Are there any questions on this? Mass flux is taken to be 0. That's a condition that is imposed. If there is no net mass flow, that is a condition. And impose a volume flux also, you get a different result. This is a condition used in standard treatment. And what you get is this. Yeah, that's what that you have to ask birds to Lightfoot. That's what I haven't really examined this problem in detail. There might be some other references which have actually handled this in a different way. This is the hodgepodge introduction. So we'll have to move on. Those pieces are already raised, right? So while I haven't had the time to really examine all this and then come up with a satisfactory solution, so I'll just leave it to the questions that I also have. This is, I have portrayed faithfully what has been given in words to Lightfoot, pointing out some of the highlighting the approximations and possible re-look at the problem. inconsistencies that I have pointed out in the Boson's approximation itself. On the one hand, treating the density as effectively a function of temperature and pressure, that's compressed here, but on the other hand, treating the pressure as a mechanical variable and actually not finally using it also. It's not used at all. And we seem to get another condition that will lead to this kind of a profile. Right? So those questions remain. I have not answered any of them. So another instance where the Boson's approximation is used indirectly, we are not going to use it directly. It's the consideration of the so-called thermal boundary layers. I'll briefly discuss that. There's also a virtual light. So what we consider is we see the flow over a flat plate. Now on top of flow effects, we also consider that the plate is maintained at a temperature T0. It might be at a higher temperature than the fluid, so the fluid is getting heated as it passes over the plate. And so on top of the flow, which is already there, which we have already considered here, we consider as T0, and then we consider the no slip boundary condition of the wall. Here the condition is T equal to T0, and here the temperature in the entering fluid is taken to be T infinity. It enters at a certain temperature uniform, and then what happens when it passes over the plate? So what we have is on top of the hydrodynamic boundary layer, we also have a thermal boundary layer, and we see how that is defined. So what Prandtl and Lightfoot point out is on account of the fact, if you now look at the energy balance equation, it will look like this. It comes with certain approximation. This is a two-dimensional variation of the temperature that is considered, but the convection to the y is as earlier this. So the convection effect in the x direction is neglected, and then you also have the viscous dissipation term, which you can easily prove to be given by this. What he points out is that in the momental balance, you have the term coming from the gravity, rho g, and there he says you would have to take into account the Boson's approximation, and that will in turn affect the results that we have already obtained for the velocity profiles, which were obtained using an isothermal condition through O. Right? So I am just going to write down the equation, which might be useful for solving problems. So what he introduces is a slightly different expression, where you have a combined effect of the hydrodynamic and y less than or equal to delta. You have to compare this. So you compare this with what we had earlier, which was 3 by 2 y over delta minus half. So he's saying that naturally, if you want to take the density, effect of temperature on the density term, that is going to modify. This is again coming from an approximate analysis. We are not going to go into the details of how this is obtained, but I just want to point out here. And finally, for the temperature effects, this should come from an approximate combined analysis based on the order of magnitude estimates that we had already for the hydrodynamics alone. So what the thermal boundary layer is defined as this is T0, right? And so finally the temperature is going to be T infinity, the bulk. So wherever that reaches T infinity, close to, you can say 99% of that is what is maybe this difference is what is referred to as the hydrodynamic the thermal boundary layer. The thermal boundary layer is also a function of x, and in delta, and this is equal to 1 for y greater than. So you can see when t becomes t infinity, that is when y will become is taken as the thermal boundary layer thickness. And further relations are given. So the delta also gets modified. So 4.64, what he has is 5.84 by REX over half. So this is again modified. It's all coming from an, I'm not going to go into the details. And interestingly, the thermal boundary layer, again using an approximate scaling analysis, can be shown to be given the Prandtl number minus 1 over 3 for delta less than or equal to 1. What greater than 1, I haven't seen the expression in words yet. So obviously this is certainly valid for when the thermal boundary layer is less than the thickness is less than or equal to the hydrodynamic boundary layer. So this leads to the you can easily infer roughly whether what will happen if for various values of the Prandtl. If a gas is Prandtl number will be of the order of 1, right? And so the thermal boundary layer will be more or less the same as the hydrodynamic thickness, whereas for liquids, then the Prandtl number will be much greater than 1, right? It's the hydrodynamic boundary layer that will be larger than the thermal boundary layer. So Prandtl number 1, because this limitation is there, so I don't know how we can extrapolate this for when delta T is less than, but this is accurate for delta less than or equal to 1, but for other cases it may give a rough idea. That's how we have to take it. Okay, so for gases, you can clearly see that delta will be of the same order. So liquids, where PR is maybe of the order of 10 or so, you can clearly see that the hydrodynamic boundary layer will be greater. Classic examples given for Prandtl number less than. What is this Prandtl number? It is Cp by K, and that can also be written as often referred to as momentum diffusivity by the thermal diffusivity. So this is for liquid metal, and here what we would have to regard, we have seen the coefficient, let's take this for liquids where the hydrodynamic boundary layer is greater than the thermal boundary layer. We have seen that the kinematic viscosity actually appears in the vorticity, which is often referred to the momentum diffusivity. We have seen that it also represents the vorticity diffusivity, the vorticity equation. It appears as a diffusion term, multiplied the Laplacian of the vorticity. So when you say that the boundary layer, the hydrodynamic boundary layer extends far into the liquid as compared to the thermal boundary layer, what we are effectively seeing is that the diffusion of vorticity is much more efficient in the case of liquids as compared to the thermal diffusion. So when we say that, because delta is large means that the layer, the range over which the, let's say this is delta, the velocity here could be V naught, right, or V infinity or whatever. So the delta is large means the thickness over which the velocity is actually less than V naught is much larger. So we have seen that to be a measure that can be sort of physically interpreted as a measure. The diffusion of the vorticity is good because we always associate vorticity with the no-slip boundary condition. Vorticity is being generated because of the presence of the wall, and if V naught is and if the velocity is actually zero here, so it's taking a longer distance to reach V naught that can be interpreted as saying that the effect of the wall persists over a larger distance. So that can be regarded as saying that the diffusion of the vorticity is being done very effectively, that the effect of the wall is felt for very large distances. That is a physical interpretation you can give. One important calculation that you can do, very analogous to the calculations we have done in the earlier cases, we calculate the force exerted on the plate by the flowing fluid. Here what he calculates is the heat transfer from the plate to the fluid the main reason for writing these expressions is to do that calculation. So heat at the plate fluid interface is where we have to calculate, and so that can be regarded as arising out of convection. So I can write this as minus q dot NdA. Right, so it's transferred from the plate to the fluid. Yes, it could be heat loss or a heat gain by the fluid. And so where we N, if you look at it as the fluid receiving heat, then the outward normal for the fluid would be in the negative y direction. So N would actually be minus Ey here. And then dA obviously would be dx, dz, with the transfer normal to that vector. And so dx, there's a minus sign here, 0 to w, 0 to L, where w is the width of the plate and L is some length that we can choose. So there's a minus here and there is a minus here, so those will get cancelled. And the q itself is given by minus k dE by dy, which was evaluated at y equal to 0. Because that is where the transfer is taking place from the plate to the fluid. So that negative sign will finally remain because this is going to cancel with this. So I can write q itself as integral 0 to w, 0 to L minus k dE by dy at y equal to 0 dx dz. You have to be able to write these unambiguously so that you don't, forget the sign. Sign convention, you have to, there is a sort of a mismatch because when we say heat input to the fluid, we reading that as Q being positive. But on the other hand, the Q, the heat flux vector, that is representing the convection heat transfer across the surface, right? That is such that minus Q dotted with N will give the heat input because N being the outward normal. So you have to understand that convention and is that heat flux vector which gives the heat input because of this negative sign. That is actually generally represented by minus k times the gradient of T by Fourier. That's a special case. It's not a very universal law as it is played. It's a constitutive relation, much like the constitutive equation for the linearly viscous fluid and so on. Right? So that is there. So that is where the fact that if the temperature gradient is in one direction, then the heat flow will be in that direction. If the temperature decrease, let's say one dimensional case in the z direction, then the heat will be flowing in that direction. That is taken care of there. Right? So you have to understand the use of the sign convention in this case. It can be somewhat confusing. So here, of course, T is a function of both x and y, but the gradient is, since it's dotted with Ey, right, because the normal here is in the y direction, so it's only the component dt by dy that will contribute. That is the point to be made here. Right? So that will finally give rise to this, and clearly there is no dependence on z anywhere. Evaluated y equal to 0, so the integral will only be over x, right? And that x dependence is coming from here. This is what I have to differentiate. We differentiate this with respect to y. So let's calculate that. based on that expression. So we are not quite worried about how that expression is got in the first place. We just using it to calculate the heat transfer. This will be a recurring calculation. How to calculate the contact force or the heat transfer by convection. It involves these kinds of integrals. You should know how to do it unambiguously. So if I take this, so clearly minus dp by dy is equal to, right? So I have minus t, and the t naught minus t, so I am going to take t naught minus t infinity to the other side. So I am differentiating then. So then that would have to be differentiated. So I get 2 over delta t, right? Minus 2 times 3y squared by delta t cube, and then plus 4y cube by delta t over 4. But I want this only at y equal to 0. So I need not really have even differentiated this. These two become 0, and so I get minus dt by dy. But y equal to 0 is given by t naught minus t infinity times 2 divided by the thermal boundary. So this is a function of x. So that's where the integral over x would come. So I can now write this as simply w times integral 0 to L dx. So that is where the dependence on x comes. So I have to simply rely on this. So delta t I will take to be Prandtl number for minus 1 over 3 times delta, which is 5.84 by Rex over half. Right? So this would be E naught x by only x dependence is coming here. So this can be written as 5.84 minus, after I have to put that in there also. This is delta, this is an x I have missed out. X I have, because delta by x is 5.84 by Rex over half. An x, and so when that is combined, I will actually get plus half here. You have to remember very clearly. Those expressions will be given to you. You don't have to remember all these coefficients 4.64 and 5.84. But so finally, then I can put all of this into the integral. So I have k times w integral 0 to L dt minus dt by dy is this. Minus dt by dy. So that would be t naught minus t. They are constants 2, and then I have 1 over delta t. So this would be divided by 5.84, and then we are power 1/3, and then I get v naught by everything I have to invert effectively, and x power minus half dx integral 0 to L. So taking all of the constants out, so this would be x power half divided by half. That would be 2 times x power half, and integrate from L to 0 to L will be L power half. Right? So I combine, put that L here, L power half into this. So that would give me the Reynolds number at L. That is what this is, raised to the power half. So I don't know if I missed out any other constant, but this is given now by 2 times k w times e naught minus e infinity 2 is missing. Yeah, where is that 2? There's a 2 here. Yeah. There's a 2 here. Right? There's another 2 here. That will become 4 divided by 5 point. Oh, that will also come in the denominator. Is it? No, that won't come. This is fine. So 4 divided by 5.84. Let me write it and you can check it. We are. So this is what we have, and this. So there has to be another 2 missing. So yeah, he has on both sides. Yeah, what this is for one side, right? So this is for one side. So this is correct actually. One side. The answer in first to x is twice this. So because as I said, we have fluids flowing all around the plate, I have made the calculation for only one side. So for one side of the plate, this is correct. So the final answer would be 2 times this, and so 2 times for both sides. And the coefficient alone, I write the 8 by 5.8, so that's 1.37 times all of this. So it's over Prandtl number over 1/3, Reynolds number over half. Those are somewhat characteristic exponents. Are there any questions on this? The treatment of this has been very brief. If you want, you can go and see how he has sort of derived these expressions using some kind of an integral balance. We are not going to get into that. It's finally an approximate fit to the actual temperature and velocity profile, as we saw in the case of the hydrodynamic formula. Also, effectively the Vx expression is coming from a fit to f prime of eta, which is obtained by solving the third order differential equation, actually non-linear equation for f, right? And then fitting the given profile of f or f prime, we get Vx as well as Vy can also be obtained similar, right? There's a calculation in the assignment that is given, which we take up in next week. Are there any questions? Yeah, if not, I think it would be prudent to have a class on Monday on top of a 2-hour class on Tuesday, which might leave open the possibility that we can wind up the course by next week. Because as per the institute official calendar, the last instructional day is the Tuesday following the next Tuesday. Your exam is on Thursday. So if we leave it as it is, we may have to continue all the way until Tuesday of the next week, which I don't want to do. At least I want to finish majority of the portion, so that maybe we can, if at all we need to meet the week after next, it's only to discuss the problem, assignment problem, which we haven't discussed in detail. So I think it's safer to have a class on Monday. Depending on how things go, then we can. I have to hand over the quiz sheets also, which I will definitely do on Tuesday. Right? I will definitely do that on Tuesday. We have an extended class. So I think we have to do with this. Monday is a regular schedule. I don't see any problem, and I think we'll just do it with the, not guarantee, but the promise that if we are proceeded well, we only have a few simple topics to cover on mass transfer. After I briefly discuss the energy balance for compressible fluids. Right? So there's not much portion to be covered, but I would still, as a security, have the Monday class and hopefully finish by next week, rather than extend it all the way until the Tuesday following next week. Right? So I think we should then meet on Monday. Right? Coming Monday, 8 o'clock, the same room. Right?